So today I'm going to sort of take you through how we are unlocking next generation of satellite gateway throughput by moving to higher frequency and higher power. As the networks scale into LEO, MEO, and GEO constellations, the uplink amplifiers and frequency converters sort of become critical enablers. And so let's go and understand what the challenges are and how we address them. I'll start with a quick introduction to Filtronic, and then I'll move on to the gateway demand trends. And sort of after that, I'll highlight some of the challenges, the design challenges in high frequency, high power systems. So in Filtronic, we're an RF technology, and we have hybrid manufacturing techniques with years of experience behind us. We sort of focus on systems that are customized to specific requirements, but we also have in mind to make those systems into building blocks so people can sort of speed up development. We operate through a vast majority of the spectrum, even though we provide solutions from anywhere from UHF to sort of D-band. We are very good at working in millimeter bands, so sort of K to D-band. We operate in the US and the UK. We have sites in both continents, and in the UK, we have 4 locations. We've got 3 design centers scattered around, and our headquarters up north in Sedgefield, which also facilitates our production. We operate in all 3 domains, surface, sky, and space. And within those domains, we provide solutions for transmitting and solutions between any combination of those platforms. And space is a hot topic these days. So we provide all sorts of ground infrastructures, payloads for telecoms and radars. Okay, so that's the marketing slides out of the way. Let's sort of start with some fun stuff. Okay, so I want to highlight that there is a huge exponential growth in ground stations. As key players in these markets put up more satellites, there are more beams, and with that, the throughput gets higher and higher. So typically, these systems are catered for in the K-band, and now people want more bandwidth. So the obvious choice would be to go up to the next spectrum, which is the Q and V band. So that's obviously goes into higher frequency, and we need to understand what the challenges are. So as we go up in frequency, I've just sort of listed a few challenges here. So you need to cater for those RF chains. We need to make sure they're linear, and there's a focus on the power that you need. Traditionally, to create these powers, the systems are based on traveling wave tube amplifiers. And as you know, they are not reliable, they have a limited lifetime, and they're expensive. They sort of don't make sense, they don't scale economically. And this is where solid-state amplifiers technologies are based on GaAs and GaN are really showing promising results. And they could be a good rival with TWTAs. So what does that mean when we go to up frequency? Well, as you know, we all know our frequency equation. As the frequency increases, then its attenuation increases. And with that, we've got atmospheric environmental conditions that add additional attenuations on top of that. So to get through that, we need more power. But with that, the systems have to tolerate the losses that you get through conductors. So this is your PCB microstrips, the dielectric losses, and the surface, even your surface finish on the waveguide can all have an impact. You got to create these high frequency signals. You need higher load. If you multiply these loads, your phase noise goes up. So there's a trade-off between what you can do to not sort of jeopardize your system figure of merits. And going through some of the challenges that other speakers talked about, when it comes to testing. Testing at these frequencies shifts the testing regimes to fixtures, waveguides, and over-the-air sort of environments. If you design something at 50 gigs, you've got to be able to have the equipment to test it at 50 gigs. So that's also presents some challenges. So here is just a summary of how we can get to these high powers. So it's a long journey to go to that, but you've got to start from down to the MMIC level. So here we got your typical MMIC design. So a lot of MMIC designers have their own challenges. We've just had, again, previous speakers sort of highlighting these factors. So with that, you've got your device limits, there's a lot of parasitic capacitive inductance, or even wire bonds that have a huge impact on your performance. Once you get that, you design this, you got to turn into a product you can test. So the next step will be to put that on a carrier. There's a lot of unmodified probing, measurements, and being able to test this reliably. After that, you got to create more of them. So panelization of these tiles are also very challenging. So making sure that you get high yield when you create these devices on wafers. Once you optimize the output power that you get from a single device, then the next challenge is to combine them. And then from that point onwards is sort of different challenges come into play. So if you combine the amplifiers, obviously you get your added combined power. But if your combiners introduce additional loss, it defeats the whole point of combining in the first place. So being able to coming up with a design that has low loss, minimum phase imbalance is a challenge there as well. And then after that, you got to package it all up. So putting these systems into a block and reliably test them, making sure they operate through the required environment is a challenge as well. And then really to go up, it's a matter of sort of putting this block systems together to get you to high frequencies, high power. So I just wanted to highlight two figure merits there. I deliberately sort of picked this plot here because it just sort of shows nicely what the challenges are. So this is one of the measurements that we did from one of the first past designs that combined 32 amplifiers to get us up to about sort of 100 watts. So it shows that we can get to 100 watts nicely. Yeah, great. But look what happens to the top of the band. You got a huge drop, which means half the power is lost. So this shows nicely that it is a challenge to come up with a consistent output power across the band, especially when you're operating at wide bandwidth. And yeah, so subsequently from one of our recent measurements from our second run, we managed to create 100 watts pretty much across the whole B band. This is another one that, again, was talked about in previous talks, EVM. So we are now dealing with high bandwidth signals, 5G, 6G, 3G PP signals, FR1, FR2, and they pack more carriers within the bandwidth. So what happens when you push these signals through an amplifier? So this graph shows when you start putting one carrier into the signal, yeah, okay, great, you got your linear performance up. But as you pack more carriers into that bandwidth, your EVM starts to drop. So if you're given a specific EVM for a system, you can see most of that is dominated by the PA. So you have to really balance it out here. How do you do that? You have to back off the power. And as you back off the power, to get the required power, you got to combine more. but there's a trade-off. How much can you combine before you run into problems with thermals and practical issues? So here are just sort of some thoughts to think about. So we talked about our 100 watts SSBA V-band that we've managed to produce recently. We've taken that into further, creating more power. So we're now creating modules that provide 200 watts and 400 watts at the V-band. So how do we do that? Well, we'll base it on our building blocks. So we take our sort of 100 watt SSPAs and then we combine them. Well, that's great. We can get the power here, but at this frequency, at these higher powers, any loss after this point here onwards will be very critical. So, for example, if you want to design a system, you have to add other stuff in front of the PA. So these are your harmonic filters, your receive reject filters, and whatnot. And if you're promising that you're going to deliver something at the flange, you're going to make sure you provide enough power to get you through these losses. And the other things that are important in this system are, for example, the gain block that goes in front of it. So you got to make sure you shift your signal level before you push it into the SSPAs, and you got to make sure you don't compress before you go to these high amplifiers. So that's the RF challenges. But what about the electronic and mechanical? Well, these are high powers. If there is any adverse load in front of it, you're going to run into problems. So protecting the users or even protecting the equipment. So there's some smart electronics that need to be designed around this to make sure everything functions properly. Okay, so then we've sort of going backwards. We've talked about high powers, and now what about high frequency wideband converters? So traditionally, I'll pick that up from a nice journal by Analog Devices. Traditionally, to create these wide bandwidth signals, you use switches, multiplexers to stack up the signal, the subbands, and create your wide bandwidth. You even sort of perhaps might look into double conversion to get you to those high frequencies. Well, when you're working in QV bands, I would say keep it simple. Double conversions add ripples and things that you don't need. Spares that might sort of degrade your system. So in these systems, although you keep it simple, then the challenge becomes a bit more focused on the individual components in that system. So you got to make sure you pick the right part to have the adequate performance. So these are your high linearity mixes, wide bandwidth power combiners that give you a nice and flat response. So we've got a few products that overcome the challenges. So we got a product for ground stations and payload. So these are sort of Ka band, Q and V frequency converters. We are now also in development in a few other systems for ground stations that take up a wide bandwidth IF and convert them to QV bands. And lastly, I'd like to sort of close the loop. So we've talked about this high IFs, but how are they generated? So as you know, by sort of key players providing really capable chips these days, we can generate high frequencies well into sort of 30 gigahertz of bandwidth. So this is the time to sort of make use of these chips to provide SDRs and modems that can create those IFs and being able to convert that into QV band with single conversion. But there are challenges here involved as well. So our roadmap here is to sort of make sure the RF stocks are behaving well. So we're creating products sort of released next year that will demo that. And then after that, we are planning to pair this up with SSPAs. So you really then you've got the SDRs with SSPAs in one sort of system package. Once you create these IFs, because they're in digital domain, it's then easy to manipulate, process this data digitally. So there's a whole community based on digital IF interoperability. And the idea is that if you got a ground station that talks diffy, and you got a modem and a SDR that talks diffy, then you can just plug them in, and everything then becomes digital. We are a part of that diffy consortium as well. So we influencing standards and protocols. So just to summarize, the gateway demand is rising. That puts a lot of pressure and opportunities for ground station infrastructure. To be able to create those systems, you've got to have adequate power amplifiers and frequency converters. And I would say to get involved in those systems, make sure you've got your sort of system compliance metrics nailed down before you start on these projects, because they're very, very important. You don't want to change them halfway through the project. Thank you very much for your attention, and thank you for intelligence.
Thank you very much. Do we have any questions? Yeah.
Thank you very much. Quick question. I think you mentioned that to achieve around 6 to 8% EVM, you needed to have 20 dB backoff, kind of. Is that in the current product, or is it?
No, it wasn't 6%.
Or maybe I got it wrong.
If I just go back. So let's say you've got an output power of a single amplifier that gets to about 35 or 32 dB on PSAT. To get that 6%, you've got to back off almost 6 or 7 dB. So you really your linear power then drops to about 28 to 27 dBm.
Okay, so around 6-7 dB. Okay, yeah, thanks.
Okay, anyone else?
Hi, my name is Dr. Azim from Filtronic. So my question is that you talk about a lot of output power, like 100+ watt at quite high frequencies. So how do you maintain the isolation between the driver and the final amplifier?
So that's sort of captured here. So as you rightly pointed out, at those high frequencies, there's tendencies for leakage. And obviously leakage from your main amplifier and drivers. So we have careful mechanical designs that will stop that. But also we have adequate RF design here to make sure we don't run into sort of oscillations and unintentional leakage.
Did you consider putting some isolators or circulators in between the amplifiers?
So we have,
just in case if any signal goes back, it should not be affecting the driver stage.
Yeah. So it's a good point. So at some of the really high frequency, you might see an isolator in the system design. But in this case, we've done our due diligence and checked that if there's any reverse output power, that power gets absorbed by the combiners that we've designed. So that reverse power will then get split equally through the combiners and the splitters, but also the PAs themselves can handle that power before they run into performance degradation.
All right, thank you very much. Cheers.